Welcome to Ask and Learn.
Alright, hello everybody. Today we're going to be doing some calculations based off of the equation for the combustion of glucose. This process is how our body derives energy from the breakdown of glucose. So first things first, assuming that the molar enthalpy of combustion, i.e. how much energy is released when glucose is combusted, is negative 2800 kilojoules. Let's say that you take in 2,400 kilocalories each day. So what amount of glucose will you need for that? So this is a pretty simple dimensional analysis. We have 2,400 kilocalories. You'll notice 1 calorie is 4.184 joules. So 1 kilocalorie is obviously 4.184 kilojoules. So we just plug this ratio in. And now that we have kilojoules, we can actually convert to moles glucose. So we say 1 mole glucose over negative 2,800 kilojoules. Sorry, we don't need the negative. The negative is just telling us that it's exothermic. But for our purposes here, for dimensional analysis, we won't need it. So putting all this together, you are going to get 3.586 moles of glucose. I'm going to assume that the 2,400 and 2,800 numbers have 4 sig figs, just because I feel like 2 sig figs would be a bit less for this problem. Okay, that's your moles glucose. Now, to get from that to your moles oxygen, all we're going to do is use our equation. We have 1 mole of glucose here, and we have 6 moles of oxygen. So 3.586 moles glucose means that we will therefore need 6 moles of O2 for each mole of glucose. So our total moles of O2 is going to be 6 times 3.586, which is 21.52 moles of O2. Okay, so that's your part A. Now let's move on to part B. So part B asks us how many moles of electrons will we need to reduce that O2 from part A. So let's bring back our equations. C6H12O6 plus 6O2 gives us 6CO2 plus 6H2O. Okay. Now let's make our equation for the reduction of oxygen. So we have 6O2 going to 6H2O. That means we need to add in 12 extra H pluses on this side, which means that we also need 12 E minus on this side. So for every 6 moles of oxygen, we're going to need 12 moles of electrons, which means that if we come back earlier, we'll see 21.52 moles of oxygen, right? Times 12 moles of electrons for every 6 moles of oxygen will then give us 43.04 moles of electrons that are needed to reduce our oxygen. All right, pretty simple, pretty straightforward. Okay, let's go on to part C. Okay, so part C asks us to find the current that travels through the body based off of the amount of electrons that we found in part B. So this is more dimensional analysis, 43.04 moles of electrons times, we have 6.022 times 10 to the 23rd electrons per mole, right? You should definitely know that ratio. And then each electron, as I've written up here, has a coulombic charge of 1.602 times 10 to the negative 19th coulombs. So we write in that ratio, and then what we're left with is 4.152 times 10 to the 6th coulombs. Okay? So this is our coulombic charge. Now to find current, well, we know that this is the amount flowing in 1 second. Sorry, this is an entire day, right? This is the combustion of glucose for the entire day. So we now need to calculate 4.152 times 10 to the 6 coulombs per 1 day. And then we just start using dimensional analysis to convert a day down. So times 1 day, 24 hours, and then 1 hour is 3,600 seconds. And so ultimately what we end up with is 4.152 divided by 24 divided by 3,600, and we will eventually get a total current of 48.06 amps running through our body at any given point in time on average. Okay, awesome. So let's move on to part D. If the standard, so now we're saying that in this electron chain, our current is 48.06, but our potential is going to be equal to 1.0 volts. So from this, we want to find the power, right? That's the watts. Okay, so the equation for power is P equals IV. And where I is current in amps and V is potential or volts. So we're going to say power is 1.0 volts times 48.06 amps, which will give us 48.06 watts. Awesome. That is your final answer. Thank you very much. Have a good day.